Hello and welcome. In this tutorial, we'll have a look at one way to perform a quick and easy approximate hand-eye calibration with MVTec HALCON. With this setup, we want to pick objects from this 3D space with a robot. We observe the scene with a 3D stereo camera. To pick the objects, we have to first convert the object coordinates from the camera's perspective into the robot's coordinate system. In this video, we will determine the homogeneous transformation matrix that allows this conversion using this adapted HDevelop example. The approach shown here is based on a calibration object that is being held by the robot. Here, we use a ping pong ball as the calibration object because it is easy to obtain and simple to locate with matching. Simultaneously, the 3D camera captures the scene, and we determine the pose of the calibration object with matching. For more information on hand-eye calibration in general, you can refer to the solution guide on 3D vision. In the first part of the example, we define various parameters that the program uses, such as the radius of the ping pong ball. This should make it easy for you to adapt the example to your own application and requirements. Then we connect to the 3D sensor, which, in this example, is a stereo camera with a built-in pattern projector. Next, we connect to the collaborative robot. There are many ways to communicate with robots. In this case, we use HALCON's generic socket communication. Now we create a model of the ping pong ball for surface-based matching. Next, as usual when working with robots, we have to consider the tool center point. The tool center point is the point where the robot's end effector touches the object. However, the robot usually only returns the coordinates of its flange, where the end effector is attached. Thus, we have to specify this offset somewhere. In our setup, the end effector transmits its offset to the robot. Thus, we only specify a small negative offset to compensate for the small suction cup we are using. Now we clear the field of view of the 3D sensor and acquire image data of the empty scene. For visualization, we query a rectified intensity image of the scene. However, the main output of this sensor are the XYZ mappings. We will use this Z image to filter out the background later. Based on the XYZ mappings and the intensity image, we can create a 3D object model of the empty scene to get a first impression of the sensor's output. Next, we attach the ping pong ball to the suction cup and move it into the scene where the camera can clearly see the ball. Then we query the current pose of the robot. Take care when converting your robot's poses into HALCON poses. Consider details like the order of rotation and translation, meters versus millimeters, degrees versus radians, and so on. The first step here should be to understand the output of the robots and sensors you are using so you can work with them in HALCON. For more information, have a look at the solution guide on 3D vision and the chapter reference of Transformations Poses. Along with the current pose of the robot, we capture the scene with the 3D sensor. To make the matching faster and more robust, we first remove some of the clutter and noise from the Z image. Then we filter the Z image using the expected minimum and maximum distance of the ping pong ball from the camera. This also gets rid of invalid points the 3D sensor might return, which often have a Z value of 0. Additionally, we filter out the background. Within this reduced scene, we then use surface-based matching to locate the ping pong ball. The result is then visualized. We can see the found ping pong ball in green in the 3D scene. You can see the pose of the ping pong ball as observed by the robot and by the 3D sensor. Additionally, we project the match into the 2D scene for a straightforward visual check. If this data looks good, we repeat this step. We need a minimum of 3 such calibration poses to calibrate the setup. However, for stable and reliable calibration results, we acquire more data. Take care to spread the calibration sphere positions widely in the 3D space. You can, of course, automate this step with predefined robot poses. This might come in handy if you have multiple similar setups or when you need to recalibrate from time to time. The approximate calibration is done here. We input the XYZ coordinates of the calibration sphere as observed by the robot and by the 3D sensor. Thereby, we compute the position of the 3D sensor relative to the robot base. Check the result with this visualization, which shows the position of the camera and the robot base. Next, the calibration poses are unified in one coordinate system and visualized. Additionally, we check the difference when computing the coordinates that we recorded previously during calibration. This gives us an impression of the precision we can expect when using the calibration for a pick-and-place application. Moreover, this might reveal outliers, where, for example, the matching might have failed. For the same reason, this procedure checks the movement of the calibration sphere in camera and robot coordinates across all acquired scenes to find inconsistencies. With all these checks done, we can test the calibration results with the robot. Thus, we place the calibration sphere somewhere in the scene. Using surface-based matching again, we locate the sphere and then determine 2 poses to approach and grasp the object. Now we move the robot to the approach pose, activate the suction cup, move to the object, back up again, and above this cup. Here, we move a bit down, drop the ball, and up again. You could use any kind of object for this pick-and-place part. It does not have to be the object you used for the calibration. You just have to consider how to best grasp it given its size, shape, and surface. This concludes this tutorial. Check out the example now in HDevelop and try it out for yourself. Thank you for watching.